Welcome to the advanced section. Now we're going to talk about feed-forward control. We've alluded to it a little bit before, but we have these disturbances and we can actually measure them ahead of time, make corrective actions about them, and actually try and eliminate them entirely from the system. So not a bad idea to take that information in before it's actually affected our process or system. So we can measure our disturbance variables and then with the preemptive action, try and negate the effects. An example of that, we normally see for a whole process, we have a set point come in, goes through the actual process, and then we have our control variable come out. Our manipulated variable is what actually makes the effect on the process from the controller. But what if our controller is now actually just the feed-forward system? So we've designed this slightly differently. So think of it as in a standard system, we would have our set point go into our controller, go to the process, make some change with the disturbance and go out. So the disturbance process still follows through the same, where that disturbance is like, okay, I'm gonna follow through here, great. But normally we would actually have some set point come in here separately that goes through a controller to the process and forward. We would then have a closed loop to be able to design that backwards because it's a feedback loop. But notice there's no feedback, only forward directions today. So based on that, our disturbance is going to go through and act as a disturbance, of course, but we're going to sample our disturbance and we're going to say, okay, let's build it into a controller. That controller then will go and make a decision to the process while it's also having the disturbance in the process. We want to cancel them out. Think about the sinusoidal part where we had one phase positive and one negative 180, cancel them out. So now we have to consider the total addition to our CV output as being in both directions. We'll call this the A direction and the B direction. So how would we think about CV then? Well, we can write CV as the sum as CV of the A and CV of the B, where CV in my A direction, that is directly dVm times GD. And in the B direction, that is my manipulative variable times my GP. But my manipulative variable is also my feed-forward controller times my dVm. So I could put those together and now have GD times dVm plus GP times MV, which is this, so times GFF times dVm. I can extract out my dVm from this and get GD plus GP times G forward system. And I can divide to get CV over dVm is equal now to GD plus GP times G feed forward control. Great. But we're designing for a perfect system. So the goal is that there is no effective change in this. We want to make sure that we want to eliminate the disturbance essentially effectively. So our goal is to make this equal to 0. Now, if that's true, then what would the feed-forward controller need to look like? Well, let's move 1 to the other side and divide. GFF equals minus GD over the division, GP. Which means that is effectively GFF is, by being the negative GD over GP, it is my manipulative variable over my dVm based on those inputs into the system directly. And that's pretty interesting to think about. That is kind of wild that we can actually just design them directly in that sense. And so how would we use this? How can we actually take information from this? Well, say that we actually had information about our GP and our GD here. So let's say potentially if we're using first order systems with time delay approximations, and maybe GD is KD e to the minus S theta D over TD S plus 1, and my GP is the same approximation, so KP e to minus S theta P over TPS plus 1. Let's solve for the system and learn more about the feed-forward controller that we would need based on these two transfer functions. Well, it's minus GD over GP, so G, my feed-forward, is minus GD over GP, so that's equal to minus GD times 1 over GP. And I write it like that because I'm actually going to now take the inverse of this one and multiply them directly. G feed forward is minus GD is KD e to minus S theta D over TD S plus 1 times the inverse of this, so TPS plus 1 over KP e to the minus S theta P. Let's group like terms so that we can try and pull out and extract a similar looking expression for my new feed forward controller transfer function. So minus KD over KP first as my gain value, multiplied by TPS plus 1 over TDS plus 1, multiplied by e to the minus S grouping of theta D minus theta P. We've just grouped together these exponential terms. And that looks like it. If we wanted to, we can rewrite this in a way that looks very much like this, just like group the things a little bit to make it look very similar, but I think it's sufficient as it is. But there's still information that we're learning from the system. So in the first part, we're seeing the effect of the gains directly in that it really just mimics this directly. The GD over GP minus is the same as the minus KD over KP, direct mimic. So effective gains are scalable, they're proportional. This is unique. This is a lead lag algorithm. And this lead lag system says that my TP will lead and my TD will lag. So this is essentially how we are deriving our process model based on what part of the system is leading to make quick changes or what's lagging, and both of which are influencing to our time delays that give us an overall feed forward time delay here based on our disturbance in the process. And this is interesting because what we're saying is, okay, well, we can quickly make a decision for the process. We're leading the system with that. But ultimately, what is the effect of our system that we're actually getting by the disturbance? So we're creating like a counter disturbance first to account for it. A lot of you probably have noise canceling headphones. Same idea. It uses both feed forward and feedback control, which we'll go into next. But the original idea came from feed forward control in that it takes information, disturbances in from your surroundings, and makes effective changes to counterbalance that. And it says, okay, well, my sound waves look like this, so I should create new sound waves that counterbalance that ahead of time and create an ultimate neutral line and essentially have zero disturbances. So pretty cool. I'm going to erase the board and write out a feed forward diagram that combines feedback control, and we're going to just, take some advantages and disadvantages of them, as this is more of an advanced system, but it's pretty cool. So see you in a second. Now we're combining feedback with feed forward. So this part may look bigger and more complicated, but you're more familiar with it probably. This is what we've just introduced. So now we're just putting them all together into one. So how would we define stability here? We have our set point coming in, we have our output, and we have our disturbance. The only thing we've added effectively is this. It's all that's new. This is still real. We've always had GD, but we're adding this, which means we're adding this. That's okay. We can tackle this. So output is based off of inputs. So our output CV has to be based off of our inputs. Well, let's start with DBM. DBM is going to pass by two directions. The first direction is fast and easy, and that's just going to be our GD times DVM. We can also think about the impact, though, of this addition here based on this direction with the process. So in order to get there, we need to think, okay, well, we're going to have two different pieces that pass through from this. We did that way. We need to now do this way. So that's going to be passing through two different feed forward and process transfer functions. And it's added to my next direction. And it's added here by GC times E, whatever this output function is that yields my manipulated variable addition there, is added by GC times E. But GC is multiplied by both E and P, because in that direction, we're going all the way forward from the set point, which has its own feedback control. So that's GC times GP times this subtraction piece, which is the set point minus my GM times CV directly. So what did we just do? We took our DVM approach in, then we took our direction here, but when we got from the first one, we had to add this piece, and this total piece is all of this. So we'll call this I. This I includes this addition point piece that we've also included here. Or I should actually say I is both of them. My apologies. This would be like I, and this one would be here. And this one would become 3 I's, which is really here. And that allows us to now think about the whole system effectively. We've already considered our feedback because we have the subtraction, no sweat. But this is a lot. This is a lot of pieces that we're considering here. So we want to solve for CV as a function of our inputs, so of DVM and our set point. That's our goal. We want to see what the overall functions are inherent to that. Oh, I'm going to move out of the way. I don't want to be in the way for you. So how can we do that? Let's group like terms. Let's try and identify where the set point is alone and DVM is alone. So CV equals GD DVM plus GP GFF DVM plus GC GP SP minus GC GP GM CV. We just expanded those terms directly. We can now move this to this side and group like terms. We'll extract already out our CV term from that. So we have a 1 plus GC GP GM equals, this term is grouped GD plus GP GFF all times DVM plus this term for my set point, GCGP times SP. So each piece, my output, my inputs, both have their own transfer functions that group for them. We can go ahead and divide this to both sides, and we're going to get the stability criteria essentially for our system. So now CV is GD plus GFF GP over 1 plus GC GP GM for my DVM plus GC GP over 1 plus GC GP GM for my set point. And ultimately, this piece here on its own, as we had it, or the division piece here, is the stability criteria. So the stability is based on that open loop system, as you remember, that 1 plus GOL system, which is why we talked about open loop again in the last lecture. And that open loop G is here. So we need to think about that. So that 1 plus GC GP GM is the stability criteria. But when we think about that, GC GP GM, well, that's just the loop. That's still talking about the open loop. The loop itself is that. Thus, huge revelation, super cool. The actual feedback control is what defines stability. Kind of crazy. And yes, our GP is influenced by these terms. That is absolutely true, 100%. But when we think about the total system, it's kind of wacky to think that the feedback control is the definition of stability. It is what defines that alone. And so there are some advantages and disadvantages. When we think about those, we might say feed forward versus feedback, pros and cons. Well, feed forward systems allow us to really compensate early for disturbances. So set disturbances essentially to 0. and no effect on stability. Pretty cool. But that does nothing to the offset. It does not at all think about offset between my set point and my CV. So we will have a hard time with that in actually generating a no offset system, something that actually gets you where you want. Feedforward can be really good, but on its own, not very effective. Now on the opposite side, feedback control gives you 0 offset, which is critical. And it can be effective for all disturbances. So that's pretty great. However, unfortunately, we have to always wait and see. So this has a strong effect on stability. And it's time consuming. So yes, you can have a combined system that would be highly effective and powerful, but Feedforward is the kind where, unfortunately on its own, not very effective, going to be honest. Unless you have a perfect set point always, it's just not going to be effective. It's a great addition piece though. So adding it on auxiliary, great. Definitely should consider that. This is a beautiful system, well-defined still, but we're just adding a new element here of this piece. And that should make sense because our set point alone looks standard. You know, you have your input piece over the total loop, and we could have done that. Same thing here, our input piece, so GD plus the other direction of GFFGP over the total input loop. We could have designed that from the start, but we took the longer route. We just thought very critically about the system and said, how would we build that out? There are some pros and cons, but ultimately, if you can combine them, you have a great system. So thank you for your time. We're going to talk about Cascade last. So see you in a bit.